first class you have talked about the direct stiffness method, which means sort of steps just to discretize the problem and get a solution in a very general way. Okay, so you got a solution, for example, for a truss problem, very simple problem, using particular postulates of mechanics of materials. But now we are going to talk about something more complex and more general, which is the variational formulation, focusing our attention in very simple finite elements. Okay, when you talk about the direct stiffness method, you were talking about steps with included the discretization of the problem, the merge, the boundary condition applications, which are all of them non-dependent or non-element dependent. So now we are going to present a variational formulation which is general for all of them, for all the finite element method, using a potential energy principle, which makes it general and much more consistent for all the formulations. Okay, we are going to present this formulation, this variational formulation, using simple elements, just to make it more and more complex every time, just to make make you understand which is the advantage of this formulation. Okay, we don't need the mechanics, we don't need the simple mechanics of materials postulation, but using a energy principle for this to take these governing equations makes the problem much more consistent, and we can arrange some convergence properties which make us be much more happy about our solution. So we're going to start using a very simple element, which is the bar member. So imagine we want to solve this problem. This is our bar element. We prescribe an axial force. We have an element which is determined by this longitudinal axis with a cross section which is the intersection of the normal plane with this longitudinal axis. So this cross section is characterized by an area value, and the axial force prescribed in this longitudinal axis, we call it x. We assume that this bar element has one intrinsic dimensionality. That means we are worried about only one dimension, x dimension. So our problem is one dimension problem, even if this bar element is placed in three-dimensional problem. Okay, so we are worried about only one dimension, which is this x behavior, and we assume that in this cross section in this longitudinal axis we can prescribe a punctual load in this extreme, right extreme, and a distributed load along this longitudinal axis characterized by this value. Let's see. Well, this Q depending on x variable, which is applied in this longitudinal axis. L is the length of this our bar element. So our one-dimensional problem behaves only in this x direction. So everything will be expressed in this x dependence on the problem. We want to solve this problem using this variational formulation. Just to, let's see. Okay, no, not okay. Okay. So the notation we're going, the variables or the variables, the magnitudes we're going to work with are first of all this primary variable, this axial displacement. This is our objective. We want to know which is the function of displacement and solution of the problem. The x is the longitudinal axis. This is the dependent, the independent variable. We call the derivatives using this notation here. I think, well, this notation, this derivative notation. Q, depending on x, is the distributed axial force. This is given by per unit of bar length. in this in the longitudinal direction. L is the total length of the bar member. E is the elastic modulus. We assume the material is elastic. The cross section, as I said, is characterized by this A value. This A value, this cross section, may be variable in the longitudinal direction, but we assume for simplicity as constant. This A times A is the axial rigidity. We assume constant, although it can be variable along the longitudinal axis. We assume our strains are infinitesimal, and these strains are related with the displacement using this derivative operator here. This derivative operator leads us to the relation, kinematic relation between strains and displacements. The axial stress are calculated assuming the Hughes load. So these sigma stresses are related with strains according using this elastic modulus. This is only one dimension, so the stresses can be explained as a elastic modulus times the strain, or the elastic modulus times the first derivative of the displacement primary variable. And finally, this internal axial force is calculated like as the stress times the cross-section area, or related to the strain, the axial rigidity times the strain, or this axial rigidity times the first derivative of the displacement. So these are our internal axial forces, and P will be our prescribed end load in one of the edges of the bar member. So, according to the presentations before, we can build a sort of diagram using the governing equations of our boundary value problem. So here we have all the ingredients of our problem placed in the proper place, just to understand which are the important things. So here we have this primary variable, this axial displacement, which are our objective function objective, related to the strains. These strains are calculated from the displacement using a kinematic relation. In our one-dimensional problem, these strains are just the derivative of the displacement. In a much more complex problem, it will be something a bit more complex. But this is the point with starting with a very simple var element. These axial strains are related with the axial force using a constitutive law. In our case, this is the elastic theory. So our axial force F is calculated as the rigidity times the strain. We can change this constitutive law, but in our formulation we don't need a very complex constitutive law, but there will be always a constitutive law between axial strains or strains and axial forces. These axial forces must assure the equilibrium with the distributed axial force applied in the bar element. So we have a governing equation including the equilibrium condition, and here we have in the right side the boundary conditions on force. So our unknowns are the yellow squares, and the given problem data that we have at the beginning are the prescribed displacements, the distributed load, and the prescribed end load. So we have three types of governing equations we must assure to solve our problem, which are the kinematic equations relating the primary variable and the strains, the constitutive law relating the axial strains and the axial force, and the equilibrium, which is the relation between the axial force, internal force, and the distributed force, external force applied, and the prescribed end loads. Okay, this is what we call Tonti diagram, which is quite useful to understand all the boundary value problem. It is common to all the problems we are going to present. So this is our bar element formulation, and we're going to make something very similar in the second, in the next hour in the class, with the plane stress problem. And in fact, we can use this Tonti diagram, these governing equations, for all the problems. This is not element dependent, so we can present this formulation for all kind of complex problems we're going to present. Okay. So let's see. We are going to start our formulation talking about this total potential energy, functional, calculated in this way. For a bar element of length L, we can calculate the internal energy using this expression. In fact, the total, the internal energy density is calculated like 1/2 the stress times the strain. This is the internal energy per unit of volume. We always talk about this total energy per unit of volume. This unit of volume is calculated like the cross section times the differential of x, which is the one which appears here. So in fact, we can start calculating this internal energy, integrating this density internal energy across all the length of the element, this L variable. So our internal energy is calculated like this integral here. Let's see if I can. Well, oh, great. So we can calculate this internal energy using this expression here, integrating this density, internal energy density, across the bar element. If we can express this force using the internal rigidity and the first derivative of the displacement, this u apostrophe, okay, our internal energy is calculated like the second one, and we reorder these terms. Our internal energy is calculated like 1/2 of the integration of this from 0 to L, this first derivative of displacement times the rigidity. This shape, this internal energy shape shown here, is perfectly extendable to all the problems. This is very simple because it's a one-dimensional problem, but in fact this internal energy will be calculated like a first derivative times the rigidity times the first derivative of the primary variable. Okay, this is our internal energy, strain energy, in our bar element. On the other hand, we have the external work. This external work calculated using departing from this axial load per unit of length. So the external work will be calculated multiplying this axial load times the displacement. This will be the external work, the density external work due to the external loads, and integrating this axial load across the bar element length from 0 to L, we have this external work due to the axial load. Apart from that, we have a punctual load, a point load in the edge of the bar element. We can have this punctual load or not, and we can express this punctual load, this point load, in the edge of the element like this, like P point load times delta Dirac in the edge of the bar element, that's x equal to L, times the displacement times differential of x. So usually we have an axial load Q, but for a general presentation of this external work, we can consider this edge load at the end. So we have this internal energy and this external work, and we can define this total potential energy like this difference between the internal energy and the external load. So this potential number is the total potential energy in our bar element. Okay? This is from the continuum point of view of the problem. Soon we're going to get to the discretization of the problem, so we finally will talk about this problem from the discrete point of view of the problem. So we start from the continuum, which is our real problem, and we're going to discretize this problem, and we're going to talk about this same total potential energy principle from the discrete point of view. Okay? So let's see what can we do with this total potential energy. First of all, we're going to talk about these kinematical admissible variations. We need it for the formulation. So we start considering this bar element with length L, And we consider a continuum, from the continuum point of view, a displacement function along this L, length of the bar element, taking into account that this displacement function must accomplish two conditions. First of all, it must be continuous along the bar element, and second, it must respect the boundary conditions. For example, you have a displacement, prescribed displacement in x equal to 0, so this displacement function must respect these boundary conditions, and the same along the bar element. We consider a variation, and a kinematically admissible variation of this displacement function. So let's consider this delta ux as an admissible variation of this displacement function. This variation must accomplish, again, these two conditions. So we call it kinematically admissible variation of the displacement function if the continuity is respected and the boundary conditions are respected as well. So if we consider this variation of the displacement function, we can calculate a variation of this total potential energy, and we call it this total potential energy principle, which states that the displacement, which is the solution of our problem, which satisfies the governing equations, that's the three governing equations we've talked about, the equilibrium and the kinematic and the constitutive flows. The solution of this problem, these governing equations, is the one which renders this total potential function stationary. That means this variation must be 0 for the displacement function solution of the problem. So this is our minimum potential energy principle, which is the one we're going to use to formulate our variational formulation to get to the governing equations of the problem in the discrete space, from the discrete point of view. Okay, so considering these admissible variations, we call it delta u of the real solution, we have a displacement function u, which is the real solution plus this delta u. This delta u satisfies this total potential energy principle, which is the one we're going to use, and we're going to do it in this way. So now we're going to cross the line and get to the discretization of the discrete space, or the discrete formulation of the problem. So let's consider our displacement function as a superposition of these discrete values of the displacement in different points of the bar length. Okay, let's consider our bar length is discretized in 4 elements, any of them with 2 nodes, and we are going to calculate the displacement in these nodes, only these nodes, in these 5 nodes. So we have a displacement function expressed as an expression using these nodal values. This is what we call a trial function. Okay, so we have 5 values of the displacement function in the nodes, and assuming these boundary conditions, for example, this node 1 is assumed as fixed, so we have a boundary condition we must respect here. This trial expansion must accomplish these kinematic admissible conditions as well, which means they must be continuous along the bar element and they must accomplish these boundary conditions. Okay, so now we have a discrete formulation of the displacement function, and we're going to translate our minimum potential energy principle to this discrete formulation we have presented. So this is our total potential energy principle, which means our variation of this principle must be 0. If we get that, we're going to get this exact solution of the displacement. We can consider that this total energy must be or can be decomposed into the contribution of these of any of these discrete elements. So if n super e is the number of elements of our bar element, this total potential energy is the summation of these contributions. So the total variation of the total potential energy will be this the addition of these contributions from any of these elements, so any of which means this any of these contributions should be 0 to assure this total potentially is stationary. So we assemble these elemental contributions to get this total potential energy computed, and we are going to get this element stiffness assembled from the variation of the internal energy, and the elemental external forces will come from the assembly of this external work. So remember that this delta P includes the internal energy and the external work. So from the internal energy we're going to get the stiffness matrix, and from the external work we're going to get the external force in a consistent way. A consistent way means that we are using a total potential energy principle to get these governing equations. Okay. Let's see. Great. So if we are talking about the discrete space, we can express this displacement function using using an interpolative functions called n, and from this element, so any of these elements we have shape functions, same number of shape functions as number of nodes. So we have if our bar element have 2 nodes, we have 2 shape functions which are characterized by using the conditions we must accomplish to have an admissible kinematic conditions in the bar element. So first condition is this shape functions must be continuous over the bar element, and the second one is that the value of these shape functions is 1 in the node and 0 in the opposite node. So we have any of these shape functions is related with one node, we have this n1. Let's see if this n1 shape function is related with this node. So this must have this 1 value in the node 1 and 0 in the node 2. And the second shape function from the node 2, same thing, must be 1 in this node and 0 in the opposite node. So the displacement in this bar element from node 1 to node 2 is characterized using this expression. So we are interpolating the displacement function using the values of the displacement in node 1 and node 2. If we get the analytic expressions for these shape functions using these conditions, we get to these expressions here, and we have for the first shape function is 1 minus x minus x1. x1 is the coordinate of this first node divided by L, which is the length of this bar element. Remember that upper L is the length of all the bar, but this finite element, not finite element, but bar element from node 1 to node 2 has length L. So we must define this shape function in this way: 1 minus the fraction from the length with respect to the total length of the element, and same with this second shape function, which is calculated using this expression here: x minus x1, coordinate from the first node, divided by L. This is a dimensionless coordinate. We call it natural coordinate. In fact, we're going to talk about natural coordinates all the time, because we don't have to worry about the position of the bar element inside the geometry. So this relation here, x minus x1 times L, we're going to call it t. T is our natural coordinate. So in fact, the shape functions are 1 minus t and t. These are the 2 shape functions, which allows us to express the displacement function all over the element, okay, for any point along this length L in the bar element. So we have a discretization of this displacement function expressed in this way, in a matrix way, using the shape functions n1 and n2 for this element, and the value of the displacement function in node 1 and node 2. So This is our discrete formulation of the displacement function. Okay, so we're going to talk about displacement, strains, and stress. So we're going to translate our discrete formulation to the strain and the stress formulas using the expressions we have seen in the first way. The axial strain is the first derivative from the displacement with respect to x. So we calculate this derivative using this discrete expression. So our shape functions which are dependent on x are the ones which are the derivatives which appear here. The nodal values are not x dependent, so they are constant. They are our unknowns, in fact, but they are not x dependent. So the derivatives affect only the shape functions. And in this case, if we remember the expression, these derivatives with respect to x are 1 time divided by L minus on y divided by L in the second case. So here we have the expression for the axial strains over one element. So 1 divided by L times minus 1, and the nodal values. This derivative matrix from the shape functions is what we call B matrix, or strain displacement matrix. Call it B, and is the one which stores the information for the strain. Okay, so we have the displacement, we have the strain, and we have now the internal energy and the stiffness matrix. We said that this internal energy is calculated like 1/2 integration in a bar element, the strain times the axial rigidity, and the strain times the differential x. Taking into account this strain is calculated as a first derivative of the displacement. So if we translate our continuum expression into a discrete expression, we get this kind of expression here. Straight here. Okay. So we have this expression here, including this axial rigidity, these x derivatives from the displacement, and this nodal value of the displacement into the integral expression. This is the internal energy for one bar element. Okay. So assuming these nodal values are constant, they are not x dependent, so they can come out from the integral. We have then this internal energy expressed like 1/2 nodal values, integral, differential x, nodal values. So we can identify these terms using this expression there on the right. We have these nodal values, and inside this integral is what we call stiffness matrix. So the stiffness matrix is the integral of the rigidity and the product of the strain displacement matrix B times B transpose. So if we calculate this matrix product, we can get to this expression here and get the integral, and this integral is what we call the stiffness matrix. So stiffness matrix is usually an integration of the strain displacement matrix times, in this case, the axial rigidity, but in general is the constitutive relation between strain and stress. Okay, so this E times A is the constitutive term, this B strain displacement matrix inside the integral, and we have this integral which leads us to the stiffness matrix of the problem. Okay, for a bar element. So here we have, if we consider, as it's usual, this axial rigidity as a constant over the element, we can take it out of the integral, and finally we get this stiffness matrix expression, axial rigidity divided by L times this order 2 matrix, which is the same result we have obtained in the last presentation, last day, using the mechanics, simple mechanics properties to solve the same problem, one-dimensional problem for a bar element. But we have some advantages here using this total potential energy formulation, which is, this is a very general way to solve the problem. So we can consider a variable cross-section area, for example. This is quite much more difficult if we use the mechanics. We have a weak form, weak expression for solve the problem, but we have a general method to find a stiffness matrix, defining a var element or defining any kind of element, calculating this internal energy and calculating this external work. So we can do this. We can use this formulation for any kind of problem, complex or not, but following the same steps. Okay. This simple difference between this stiffness matrix and the one you have found last day, which is the meaning of this L here. This L here. This L here. Well, this L dividing the axial rigidity. It has a physical meaning, which is the length of our member, our finite element member, which is the length of the discretization we have considered in our bar element discretization. Okay, which is not the same as the L we have found last day, which is the length of all the bar. Okay, yeah.
I think the general way to solve any problem is the last one in slide 12, which is the integral form. Because if you have a different kind of cross section, for example, the cross section along the was different or was has variation, we should integrate.
Of course. This is a particular case. This is a particular result which axial rigidity is constant. You get out. Yeah, this is a particular case. This is the general case. This is the general case. But I'm not talking about this integral. I'm talking about all the formulations. So discretization, internal energy, external work, minimum total potential energy. We get this stiffness matrix. Okay. This is a general stiffness matrix. This is a particular solution. But this is a general solution. Well, it's a general solution for our bar element. But I'm not talking about this expression, this integral A divided by L squared. No. I'm talking about the method. I'm talking about this minimization of this total potential energy. I mean, second hour, we're going to talk about plane stress problem, for example, or three-dimensional problem, or any kind of problem. If you're able to formulate this internal energy and external work, you build a total potential energy functional, you get the minimum, and this minimum will lead you to an expression similar to this. This expression lead you to the equations you must solve to get the solution of the problem. Okay, so we must understand this formulation like a general formulation. The point is that if you use an energy potential, this way to solve the problem assures you some kind of properties, convergence, for example, and these sort of things. We are going to talk in the next days. Okay, but it's not a question of get this integral expression, but the method, the steps we have shown. Okay, in fact, we are not finished yet. This is the stiffness matrix coming from the internal energy. Okay, this is a particular solution, of course, when axial rigidity is constant. It is quite useful that it is constant, but if it's not, we must make the integral, of course. This is a particular solution, and if we make this same formulation in a much more complex problem, we'll get something similar. There will be a sort of axial rigidity, but not axial. There will be a rigid term. There will be a length of the bar of the element. There will be a matrix. Okay, there will be an integral, but we are going to make the same steps to get this solution, this formulation, this variational formulation. Okay, as I told, we are not finished because we must talk about the consistent nodal force vector, which is the other part of the formulation. We have talked about this external work, which is the axial force times the displacement in the continuum way, in the continuum point of view. So if we cross the line and get to the discrete expression for this displacement, look. this displacement was expressed using this shape function matrix times the nodal values u super e. These shape functions were 1 minus chi and chi, which are the natural coordinates, and we can calculate this external work like the nodal values transposed vector times this vector f, which comes from these integrals. So we have a sort of similar expression for the external work. The nodal values times an integral. This integral is what we call this force, external force vector, consistent nodal force vector coming from the external work, and which is the second part of this total potential energy. So taking into account this displacement is arbitrary, this consistent nodal vector is calculated this way. Remember that this natural coordinate is the fraction of the length of the bar element divided by the total length of this bar element. So we can calculate this this nodal force vector in a consistent way coming from this total potential energy postulation. Okay, so now we have the, well, in this case, in the particular solution, considering this axial load as a constant, it's a particular solution. This nodal force vector is calculated this way. So we make the integral of these natural coordinates. Remember, these natural coordinates were sort of triangle over the element. So this integral is always 1/2. So we have a nodal force vector for a constant value of q, which are q times L divided by 2. But assuming this constant value of q, the axial load and the axial rigidity. So this will be the solution for the external work translated into a nodal force vector. And now we can get to the minimization of total potential energy. That was our total potential energy. So we have calculated this internal energy in this external work. So we get to the minimization of this potential energy, and we get this expression here. So we make this this operation, and we finally get to this expression. Be great if I got.
Don't you include the fundamental forces?
Yeah, we could include this, not in this expression, but we have another integral in this external work. So this punctual force will be included in the nodal external, in this FA nodal external vector. Okay. Well, finally, if we want to get the solution of this minimization total potential energy, taking into account that this nodal displacement is arbitrary, to assure this solution, this expression here equal to 0, we must guarantee that this term inside the brackets is 0. So this definiteness matrix times the nodal displacement minus nodal external nodal force vector is equal to 0. So we have finally got to the equations, to the equations we must solve to get the solution of the problem. This is the relation between the nodal movements and the internal forces using this stiffness matrix here, which is the same solution you got using the mechanics to get the solution of a discretized problem using the direct stiffness method. So this is the direct stiffness method, but using a variational principle, and we get the same shape, the same solution for our problem. Take into account that this is an expression for a one var element, so one element in the discretization of the problem. Okay, for example, this is a quite interesting example where some things are shown using this discrete equation, this discrete solution for our problem. Imagine we have this bar here, which length is 2 times L and L, and in the second part we have an axial load applied, which is Q times divided by L. So and we assume that the rigidity is E times the cross-section A divided by L. If we get the continuum solution of this problem, this analytic solution will show a diagram like this. We have a constant term in the first half and a linear solution for the internal axial force in the second one. And the displacement field solution of this problem is like that. So it's linear in the first half and parabolic in the second half with these values, Q divided by K and 3 divided by 2 times Q divided by the axial rigidity. Okay. So this is the real solution. So what we have with our discrete problem, the solution of our discrete problem, which give us the solution in the nodes. So we're going to get the displacement in the nodes, or in the internal forces in the nodes, and these sort of things. And this is what we get if we solve the problem using, remember, this expression here. So this discrete expression leads us to this solution. What happens with the external forces? Well, the external forces are the ones there, Q, which is Q divided by L. So we have 1/2 of this total force applied in the node 2 and node 3. The reaction here will be Q, of course. So these are the external forces got in the nodes. If we get to the forces on the nodes in equilibrium, internal equilibrium, we get this relation. These blue ones are the forces applied, got in the solution of the problem with the discretized equations. So we get in this node Q, which is in equilibrium with the external force. We have here Q in this left element and 1/2 of Q in the right element in this node 2. And same in node 3. So these forces on the nodes are in equilibrium. But we're talking about the nodes. What happened in the elements? We have the same thing in the elements. We are considering these forces over the elements. We got this Q and Q in the first element, so we have an equilibrium here. But look, here we have 1/2 and 1/2 of Q in node 2 and 3, which is not in equilibrium with the axial load here, applied here in the second half. So this discretization of the problem leads to results in this way. So our total potential energy principle, the minimization, assures or guarantees that the forces are equilibrium in the nodes and external forces are in equilibrium in the nodes, but not in the elements. We are not sure about this equilibrium here because we are talking about the displacements in the nodes. In fact, our discretization in these two elements in this problem lead us to this internal axial force, which is constant in the first half and is constant in the second half, which actually it's linear in this second half. Okay, so we have in an average we have the same result, but the representation of the internal axial force is not exact. Okay, we are waiting for this result. Okay, linear and constant. But we get this solution in the discretization or in the discrete problem. And same thing with the displacement field. So we get the real solution in the nodes for the displacement, but not the behavior in the elements, because here it's linear. In the second half we were expecting a parabolic representation. So the discretization is a very important part in this solution of the problem. If our discretization is finer and finer, this solution will approach the real solution, the analytic solution. But the only thing we are sure is that we get the real solution in the nodes for the external forces and above all for the internal forces, but not in the elements. Okay? But anyway, the important thing is that we have a variational formulation, a variational method using this total potential energy principle to get to a stiffness relation between these nodal displacements and these nodal vector forces expressed in the nodes in the discrete problem. So we solve the continuum problem using a discrete approximation, and we have steps to follow to get these problem equations to solve and to get an approximate solution for the displacement. The finer is our discretization, more approach, the better will be the approximation to the analytic solution we get, as it is shown in these slides. Okay, and I think this is everything for this third presentation. This third presentation of the course. Okay, this is what I wanted to explain you in the first hour. And now, if you got some questions, if not, we can stop a bit, about 10 minutes. Okay, and we restart again. And we're going to talk about the plane stress. Here we have done this variational formulation for a very, very simple bar element discretization. Okay, we're going to extend this variational formulation for a more complex problem, which is the plane stress.